All right. Welcome to episode 37 of Roid Range. We're going to talk about gimbals today. But before we get into gimbals and what they are, I'm going to welcome Kieran back to the show.
Hello.
Kieran is on our flight software team. This is your second or third?
Second.
Second. Okay, cool. So you're quickly becoming a veteran.
I guess so.
Okay. I guess at 5 we'll just get you jackets and stuff like that.
Oh, that would be nice.
Yeah. Okay. All right. Awesome. Ray, you can help design the jackets. And then also first timer is Emerson.
Hello.
Emerson, welcome to the show. Before
Thank
we
you.
start talking about gimbals, introduce yourself. Who are you? What do you work on here? And more importantly, how did you find your way to AstroForge?
Sure. So my name's Emerson. I'm a guidance, navigation, and control engineer. And before this, I was working at the University of Toronto Space Flight Laboratory in Canada. And I learned about AstroForge. I thought this was a really cool mission. This was a really cool project and idea. And it had some great people behind the idea. So I said, I want to be part of that. And
Okay.
here I am.
All right. Why guidance, navigation, and control? What got you interested in this in the first place?
Yeah, so it's been really a kind of roundabout way that I've got into GNC. So my undergrad was in mechanical engineering,
Okay.
and I was part of a space team as part of that, where I worked on rockets. So I thought for a long time that I'd be really interested in more in specifically propulsion.
Okay.
And I did a lot with relation to fluids and different things as they relate to propulsion. Did research in that. But then one of the things that frustrated me about fluid research, specifically like the computational side of it, was that you really needed kind of a supercomputer or very powerful computers in order to be able to actually do things on your own. Because I like to play around with these kind of things on my own to be able to actually implement something and run it and do all of that. Because I think by actually doing it, you learn a lot from it. And I got very frustrated at the fact that it was very difficult to do that effectively without a supercomputer and fluids. And so I found out in my last year of my undergrad about like GNC. I did my undergrad thesis in GNC, and I learned a lot from that. Shout out to Professor Demarin. But
That might be the first academic shout out we've had, which I'm here for. So yeah, okay.
Yeah. And I became really fascinated with that because I was able to write and do these GNC algorithms from my little laptop. And these were the same kind of things that were running on spacecraft. It was not lower fidelity. It was the same things. And that really fascinated me and allowed me to learn a lot about it. So when I did my master's, I focused a lot on GNC. Shout out to Professor Robert Z. And so, learned a lot from that.
Okay.
And worked there for a bit after I graduated, and now I'm here.
All right. Awesome. You got any of the professors you want to shout out while we're at it?
You know what? Professors wise, I think think that's enough.
Okay. All right. Cool. Well, I don't believe you, but we'll see. We'll see who else comes up during the rest of this.
We'll see.
All right. We're going to talk about gimbals today, but really gimbals is a part of a story in the overall thing, which is how do we point our spacecraft, right? Which is moderately important since once we get off the rocket, we actually need to go somewhere and not just hang out. I think would love one of you to sort of talk about why pointing is different on Deep Space 2 than it is Odin, right? So at a high level, why is this a different process now?
Right. So, okay, I'll take that question then. So in some ways, pointing really it's staying largely the same, but in other ways, it's changing. So what is staying the same is the fact that We are using reaction wheels to primarily actuate the spacecraft. That's staying the same, but what is changing is how do we then desaturate these reaction wheels, and how do we actually change our trajectory? And that's driven through this new propulsion system, which then feeds on to the gimbal and all these stuff which are connected.
Okay, so you said two words in there: is, actuate and desaturate. Just like
Yes.
one-on-one for anybody who doesn't understand that and isn't a GNC engineer.
Yeah. So the explanation, so desaturating is basically when you're in space, in any kind of orbit, you normally experience different kind of disturbances. So one of the things that we experience primarily in deep space is solar radiation pressure. So the sun's photons kind of are hitting the spacecraft body and are imparting their momentum into the spacecraft. And what that does is it kind of causes the spacecraft to speed up a little bit, to start kind of wobbling a little bit. But this is absorbed by the reaction wheels, which counter these disturbances. But these wheels will keep increasing and increasing and increasing speed as they absorb more disturbances. And at a certain point, a wheel can only spin so fast. And when it's spun up to the limit, if it gets hit with more disturbances, it'll just spin out of control. The whole
Okay.
spacecraft will spin out of control. So you need to be able to reduce the speed of these reaction wheels. And that whole process is called desaturation, because you are essentially, and that whole process is essentially decreasing the angular momentum of the spacecraft.
Got it.
So that's desaturation. The other thing, the translation, well, that's just we're using the thruster to also allow us to actually get to the asteroids. So it's that process of uh, kind of firing the thruster to be able to get into an orbit and make different corrections and rendezvous with the asteroid eventually.
Okay. And on Odin, we actually used a different thruster system, right? So we were chemical propulsion. How many thrusters did we have?
5.
5. Okay.
Yeah.
And as we switched to electric propulsion, how is it changing? Like outside of the obvious of like it's electric, like how is
Yeah.
that changing the actual physical configuration of the thrusters?
Yeah. So I a bunch of things are changing, but uh, really kind of some of the key things is the fact that we're simplifying a lot our plumbing system. So before we needed a bunch of different tanks to feed into these 5 different thrusters that involved a lot of feed lines, a lot of plumbing. This all has been reduced and streamlined a lot.
Because you need both an oxidizer and a propellant for chemical
Exactly.
propulsion.
Yeah, yeah. So like that is actually a key thing, and uh, with electric propulsion, we really only need one propellant. So we're using xenon, and that basically causes this whole plumbing to be simplified quite a bit.
Okay. Got it. And so why no gimbal when it comes to chemical propulsion?
So I mean, we could have done that, and there are different systems that do that. So, if you think of a traditional rocket, like your SpaceX rockets, your the space shuttle, all of these rockets had these chemical propulsion systems on gimbals. Uh, it just so happened that with this particular manufacturer that we bought this chemical propulsion system from, their layout was more about um, not using a gimbal. So it was just in kind of a static structure. And yeah, so it didn't really necessitate this.
Got it.
And so is that why we had 5 thrusters instead of one.
Right. Yeah. So because the thing with that is now that we have two thrusters, we really need to be able to point these thrusters in a direction that we want. Whereas before, what we could do is we could just fire these thrusters in different specific configurations, in different pulses, and this would eventually equate to generating like a torque or a thrust in the direction that we wanted.
So you'd fire thrusters on one side of spacecraft to spin that way, and then fire
Exactly.
them on the other. to spin
Yeah,
the other
yeah.
way.
And so, but what we have now is uh, we're really only going to be using one of these electric propulsion systems at a time. So we're using a Hall thruster. So by dropping these number from 5 thrusters to 1 thruster, now if we just kept this thruster still and we weren't able to move it, we wouldn't be able to uh, produce torque in different ways or like do any of the things that we did with this five propulsion system configuration.
We'd only be able to translate, as
Yeah,
you're saying.
yeah, essentially. So that's why we need the gimbal to be able to point in different directions.
To generate torque.
Exactly. Yeah,
Yeah.
yeah.
Okay. And then you said we're only using one at a time. Is there why is that? And is there a scenario when we fire both thrusters?
So there's never going to be a time when we're going to be firing both thrusters. We're only going to be firing one at a time. The reason we have two is for redundancy.
Okay.
In case one of these thrusters something happens to it, we don't know. But that's mostly and also the reason why we're not using two at a time is because, and Kieran can speak more about this because there's more on the electrical side, but these thrusters require an enormous amount of energy. I think it's like 1,000 watts. And
Yeah.
so like we don't even have we wouldn't have the electrical like
The electrical subsystem is not sized correctly
Exactly.
to be able to fire both thrusters simultaneously
Exactly.
at maximum power.
Got
The
it.
thrusters do have several different power modes. I think we can step all the way down to 600 watts, and I think the maximum is somewhere around
right.
1200 watts.
Yeah, it's something
So
like that.
we have discussed firing them both at the same time at the minimum power mode, but there's really no reason to do that.
Got it.
Right, because also the efficiency changes, and the efficiency is one thing that I didn't mention with this change of chemical to electric propulsion system, and that was really the main reason that we wanted to change. So
Got it.
basically, chemical propulsion systems will always be less efficient than electric propulsion systems. And so this is measured by something called the specific impulse.
Okay.
And basically, this is just kind of like in your car, your miles per gallon. So chemical systems will always have a lower miles per gallon compared to an electric propulsion system. So what this translates to is if we want to go really far to reach an asteroid that is tremendously far, we're going to have to fire the thruster quite a bit. If we wanted to stick with chemical propulsion systems, we would need to increase the amount of propellant by a whole lot
Yep.
compared to what we have now. So with this electric propulsion system, we're able to decrease the amount of propellant that we have to then be able to put other kind of instruments and allocate the mass differently throughout the spacecraft. It doesn't all just have to be, the mass doesn't all just have to be propellant.
Got it. Okay, so this is super helpful. So we have a overall more efficient, if you want to use the analogy of like we get more miles per gallon
Yeah.
effectively on our propulsion system. We have two thrusters. Each thruster will have a gimbal.
Yes.
Okay. And then I guess now let's like talk a little bit more like let's start first with like mechanically, what is this gimbal actually like? What is this? Like, let's take it away from the sort of abstracted word and just describe it as like its components, basically.
So it's basically like 3 scissor lifts,
Okay.
and then
Like
those
scissor lifts, like we use in the shop floor.
Yep,
Like just
pretty
yeah,
much
okay,
exactly.
Cool.
And then there's a ring that sits on top of those 3 scissor lifts.
Yep.
And then that ring mechanically interfaces with the thruster. And so, and then those 3 scissor lifts are driven by 3 stepper motors.
Okay.
And so through that, we can achieve all the angles we need. What's the maximum angle? Like 23?
It's 23.8 degrees.
So maximum angle on any one lift of 23.8 degrees
Of the whole
of the
sort
whole
of
thing. Sorry. Yeah.
ring.
Okay.
Yeah.
Got it. Okay. Cool. So it arrives. We just bolt it onto the bottom of the spacecraft, attach it to the thruster, and it works. Right. That's exactly
Yeah,
how
I
that
mean,
one
pretty
works.
much building spacecraft's that easy.
Yeah.
I
Okay.
don't know why more people.
All right. So Kieran, you're going to represent the flight software side of this. You're going to represent the GNC side. Like we get the gimbal in our shop floor. Like what have y'all been up to with it?
So we bought the gimbal, and then we also bought motors that attach to the gimbal.
Okay.
So you have to drive motors with special electrical circuitry. You can't just hook them up to power.
Yep.
So we actually developed a motor controller in-house.
Okay.
It uses a lot of just COTS off-the-shelf parts, but we're using like the industrial variants, and there's other hardening that goes into the design of this motor controller. So I actually I'm the one that's writing the software to interface with this motor controller and tell it what to do.
Got it.
Handle all the errors that come out of the motor controller. It's very nice. The motor controller can monitor a lot of things about the motor for you, sort of autonomously, and then you can pass that logic up higher level. So things like temperature. So like if the motor controller overheats, it'll just let you know. It has inbuilt temperature sensors. If like the wires that are going to the motor physically disconnect or get severed, who knows?
Yeah.
The motor controller will let you know, hey, I can't, actually interface with the motor anymore. So yeah, my job is all about reading those flags and then passing them up further, and then accepting commands from Emerson's GNC stack, and passing them along to the motors.
Sure. So I guess that transitions into what the GNC has been up to. And so when we got this gimbal, it wasn't with a lot of information. So really the key thing that the gimbal is doing, what it should do, is that the GNC system should send a direction, a pointing command, and the gimbal should point in that particular direction. So at first we thought, maybe it already has something like that built in. But really what was given to us was just a completely it was just a mechanical system with no kind of intelligence whatsoever. So the question then becomes is, if you have these motors, which are, so when the motor turns, there's a lead screw attached to this motor, and the lead screw then is attached to the scissor lift, and the scissor lift raises and lowers. So how do you go basically from the number of turns that the motor is spinning to the direction that you want to point at? And this this whole thing, it becomes very complicated very fast. The way that this was basically done was we separated this into 2 parts. First, it was finding a relation between the number of turns and the height of that the different scissor lifts would raise to. And then once you have these heights of the different scissor lifts, is how do you then translate that from heights to pointing direction?
And when you say pointing direction, so talk about what's in the command that you send it. Are you sending it just like Cartesian coordinates? Like what are you actually sending it to give it a pointing direction?
Yeah. So, well, the pointing direction comes from the GNC system. It comes where we're basically wanted to point in a specific direction, we send it Cartesian, like a vector
Okay.
in the body frame.
Okay.
So we're saying we want you to point in this particular direction, and then what the gimbal then has to figure out is how to change these number of turns to be able to point in this particular direction.
Got it. Okay, cool. That's super helpful.
Yeah. And so the thing is that it turns out that there's like an infinite number of different combinations in which you can raise or lower these different motors to be able to achieve the same pointing direction. So
Yeah,
the last part,
Just to jump in here, like,
yeah,
Emerson gave me pre-reading for this to say, like, hey, here's some context.
Yeah.
And he basically sent me like a 40-page math proof with like 12 hours to digest it.
yeah.
So I can say, like, yes, it seems like there's an infinite number of combinations in order to get there.
Yeah. And it's a fascinating problem. It's a really interesting problem. It's also interesting, the problem itself and all this, because I think it involves a lot of things that I think people normally don't. I think sometimes people don't see the applicability of math
Mm-hmm.
kind of in the everyday world.
Yep.
You know, there was always that thing I remember in high school. People would say, why are we even learning trigonometry? I'm never gonna use this. That
So what did you apply specifically while you were
what
you were designing this
oh
process?
well, there was a lot of trigonometry, and I'm sure Chap could attest to this.
Yep.
There are a lot of coses and sines and tans, and like all of that stuff is related, and being able to then just use math and apply all this to get to a actual solution to these things is really quite fascinating.
And so, like, how did you bound this? Were you trying to say, like, I want the minimum number of like turns from any particular screw? Like if there's an infinite possibility here, how do you start to put some amount of constraints so that you can even start to solve this problem?
Right. Yeah. So actually, that was really the key thing, because we knew that there were all of these different combinations. So the first thing that I looked at and that I evaluated was, okay, well, what if we try to find the lowest possible number of turns, like the lowest effort, to go from any one combination to another completely random combination? And so that I did this first, but the problem with that approach was that it essentially required an optimization algorithm to be run um, online, like live on, like as the spacecraft is flying, and those kind of things, you don't really have any guaranteed proofs the way that it was done that it will find a solution. Especially, you don't have like a guarantee that it will find a solution within a specific time constraint, and that's really a critical thing. So the next thing that I looked at was, how do we actually not how do we pre-solve a solution, calculate a solution on the ground, and upload this solution so that instead of having to calculate anything, it just looks up the solution from a table. It just looks up what is the solution to this. So to actually put that concretely, what this is we essentially have given a pointing direction that we want to point at. There are these lookup tables on the flight computer, which each motor will look up, oh, I want to point in this direction. That means that I have to turn to 2,000 turns. And the next motor will say, okay, I'm pointing in the same direction. That means I have to point to 3,000 turns. And the third motor says, okay, I have to point to 6,000 turns. And so that was basically then the problem that had to be solved is how to actually create this lookup table for these three motors, such that like this could be done well.
And in these lookup tables, like I'm assuming that you're not doing it as simply as like motor one has to do X number of turns, motor two does number Y, and motor three does number Z, right? There's some amount of interaction between the two in order to get any particular orientation.
Right. So, but that's the thing. So that was really the thing that like I wanted to solve on the ground was figuring all that out ahead of time.
Got it.
Because you're right, like there is a very like all of these things are very tightly coupled. So if motor 1 is at let's say 6,000 turns, that means that motor B and C can be like within a certain range to be able to operate and to be feasible. And all that was figured out ahead of time.
Got it. Got it. To ask the dangerous question, like, are there people who build gimbals with this type of like, I'm just going to call it OS because that sort of sounds like what you're building effectively? Or did we just decide to take on the brain damage of building our own because we wanted to do that?
Right. So from my understanding, we actually there really aren't that many, or actually I think that there might only be really one or two manufacturers that can create a gimbal of this size of what we wanted. So it's kind of a small size, and that was we're able to meet the time constraints of what we wanted. So we need to launch the spacecraft fast. So we can't wait 2 years for a delivery of a gimbal, sometime in the future. So we needed something that would come now.
Yep.
And I think that there might have only been one possibility, like one manufacturer that met this. And so that was the one that we had to deal with.
Got it.
And would other manufacturers like provide a lookup table or some set of equations?
I'm sure that like this kind of stuff might have been done in-house. I think this solution and the lookup table might have been something that was more, maybe other people do this. This kind of thing, it's not like gimbaling, and these solutions are such a hot topic that everyone's talking about.
It's a pretty solved problem, you're saying?
Well, no, it's like no one talks about this or like
Oh.
how to do this. And so, I mean, and there's so many ways that this could be done. And it's possible that like other manufacturers and stuff would just essentially do the first thing that I did was just solve an optimization
Yeah.
within the computer and then just give that to you. But just kind of hide this behind kind of a closed service. What we did though was do something a lot more efficient with guarantees, which is kind of the rare thing. You usually don't get these kind of guarantees ahead of time.
Yeah, the lookup table is constant time.
Constant time. Yeah, that's true. That's true.
Okay, so what like this sounds fairly complex. Like, what have you learned that surprised you along the way, and what was easier than you thought it was going to be?
Well, honestly, when I first started looking at this problem, I didn't realize how deep it was gonna go. It's
Sounds
kind of like
a
that.
classic AstroForge problem. Like,
Yeah,
didn't realize this was going to be a
Yeah, or
X number of hour
it's that
project.
kind of Dunning-Kruger effect that it's like when you first look at something that you know nothing about, you assume, oh, this is gonna be so easy. Like this isn't gonna take time at all. But the fact of the matter was that like to do it properly, to do it correctly, especially because like nothing was given to us in like with respect to these relations, these geometric relations, how we could relate these things to each other. All this had to be derived from scratch. And then we had to be sure of these derivations.
Mm-hmm.
And so The surprising part was just how kind of is the rabbit holes to be able to get this to be really correct.
Yeah. And so it sounds like you're like at the end of the day, what you're trying to solve here are two distinct but like related problems, which are like you need to be able to do trajectory change, you need to be able to do some sort of like rotation correction, right?
Yeah, essentially.
And is like so as you start to move into testing, which is I'm sure where Kieran you come more in, like how like talk about like where we are in the testing and what's been difficult in that.
So we run continuous tests with all of our flight software. So that basically means like whenever we make a change, we test that change. We have a set of test cases, and then we run those against existing hardware. So we've put a gimbal on a bench, and Emerson wrote some test cases. He has some vectors, and then Emerson also has a feedback mechanism with an inclinometer. So basically, whenever we change the software in a significant way, we'll run the test case again, and we'll now make sure that the gimbal actually reaches these expected positions with expected error as well.
Got it. And this is probably one of the few places that we're like, this is truly new ground for this flight software team as well. Because like you did a lot of work with Odin, but this was not part of this was, I'm guessing this wasn't in scope for Odin's flight software.
Well, we had motors very similar to this
Okay.
on Odin as well, with the solar array articulators.
Okay.
So actually, we'll be using the same motor controller and the same type of motors in DeepSpace 2's solar
Oh, got it.
articulators.
Okay.
It's all kind of just motors controlling motors.
Okay.
Pretty sim at the end of the day.
All right. So you're telling me I'm off on that one. All right, cool. I'll take that.
The big new thing about this is Emerson's lookup table.
Yeah. Okay. And then what are the failure modes and what are the edge cases that you're looking for in those?
Well, I
Hmm.
mean,
I can talk about the
Yeah.
big one. So
He's like, I've got something ready.
we're using stepper motors for this, right? And our stepper motors don't have encoders.
Okay.
So we're so an encoder would tell you like you would put the encoder on the shaft of the motor, and then whenever the shaft rotates, the encoder builds up a value.
Mhm.
So you actually know like how much you've rotated. Absolutely. So we're not using encoders.
Okay.
So we basically have very little idea on how the motor is rotating. But we're using stepper motors. So stepper motors are not a continuous rotation.
Okay.
They rotate in completely discrete steps.
Okay.
And that's controlled by the motor controller driver. So really, if you start from 0 and you rotate by, 1, 2, 3, 4 steps, you're always going to rotate by 4 steps due to the nature of the motor. So the problem is you have to make sure you start from 0. And then also if there's like something blocking you from rotating to 4 steps, like say you get stopped at step 2, the motor's still going to think it goes to 4 steps. And now you're off by 2 steps. And there's no way for you to possibly know that.
so now you're pointing in a
Now
different
you're
direction.
pointing in a direction that you don't expect
Yeah.
at the higher level. So using these stepper motors is one of the challenges we'll have to overcome operationally. And basically, we'll just have to make sure that the gimbal is always homed, which means it make sure it always goes down to 0 and you always start from 0 position. And then we'll also be continuously monitoring the motor controller telemetry to see if there's any indications that it stalled or hit something, or like the motor's broke,
Yep.
or we lost power. That would cause us to get out of sync from where we expect.
Got it.
And the edge case with relation or things to watch out for with the GNC system is, well, one of the things is all the mathematical models that were built up to be able to predict the motion and to point it at a specific angle kind of assumes a perfect mechanism, but all mechanisms have slop within it. So, for example, this mechanism has these kind of gears that kind of engage, but gears have kind of backlash and they have like different things that happen, and we also have a spherical bearing. And what could happen with the spherical bearing is that there might be some slip in an area which we might not expect. It might rotate a specific way. So really that is exactly why we have this kind of closed loop testing
Yep.
where we essentially, like as Kieran described, we have the gimbal and we're mounting an inclinometer to the gimbal, commanding it to a specific region, and then measuring the result from the inclinometer, from the sensor, and asking it, okay, we think that it's pointing in this direction. Is it actually
Yep.
pointing in this direction, or is it pointing in a different direction? And if it is different, then what's the error between
Yep.
that? And so by doing that across kind of the whole range of steps that we're expected to go to, then we can characterize this error
Yep.
over the whole range, and we can characterize the repeatability of this error. So we can be really confident ahead of time that, okay, when we tell it to point in this direction, we'll be, we can be confident we are pointing in this direction, barring any kind of slippage with the different motors, as Kieran said. And we'll know, well, the error is plus minus some small amount of, some fraction of a degree.
Cool. I want to go back to one thing you talked about that I think we glossed over a little bit. You said you just generated a lookup table. Like, what does that actually mean? Like, there's probably a lot more work that went into it than that casual statement.
Yeah. So basically, the way that this was done was if you, for example, want to point in, like, let's just say this particular direction, we know that in that particular direction, if we take one of our motors, motor A, we can have this motor A be from anywhere from, let's say, 1,000 steps to 2,000 steps. And within a specific range, the other two motors can find what is their number of steps in order to be able to reach that direction. But this range of validity changes for every single value throughout the entire of where you want to point. And so what we had to do is we had to decide, well, what is the best range of these values? And so I was thinking about this problem, and what this problem really kind of is how do we find a smooth surface that is able to satisfy all of these different constraints? And so what you can picture with that is like, it's basically this lookup table in 2 dimensions. It's basically like a mountain peak, and it has like, depending on the values that you pick, it can be really ragged. And if it's really ragged and it's really pointy, what that essentially translates to is that when we want to point in one particular direction, and let's say we want to change that direction just a tiny bit, if the lookup table isn't done properly, then it could mean that changing by a very small offset could reconfigure the entire set of motors into a very different orientation, like into a very different position, which stresses the motors. It takes a long time. And so what I did was I looked at what is a way that we can essentially smooth out this surface as much as possible. And so then it becomes a problem of how do we actually put that into math? So how do we actually evaluate the smoothness of a surface, and how do we minimize the curvature of a surface? How do we maximize the smoothness? And so this was done through optimization ahead of time to find a solution of essentially minimum curvature. And this was done by evaluating like something that we call like the bending energy of this surface. And so by optimizing that through all of the values of this two-dimensional kind of grid mountain. By optimizing that all at the same time, we can find one solution that works for everything. And what this means now that we have a really great solution, it means that when we're, let's say, changing the pointing of where we're pointing, let's say we're pointing in one direction, we start kind of rotating where we want to point a little bit, it means that the motors have to do just a minimum amount of work to be able to achieve that. And that means we prolong the life of these gimbals, we minimize the time required to do this, and it just creates a better system overall.
Awesome. Well, I think we've covered everything that we wanted to around gimbals. Thank you for all of that, and thank you for making me read the longest trigonometry proof that I've had to read in a very, very, very long time. With that, let's go on to the mailbag. So we just got a couple questions, and I think this works out nicely because I think we've got a question for each of you. So I'm going to assume this is going to Kieran, but this is from Daniel. Regarding the selfie camera's chunking system, does the system allow for dynamic prioritization? By that, I mean flagging critical telemetry chunks to send before high-end res images if a contact window is cut short.
Yes.
You have more words for that.
So the chunking system is applied to basically everything that's coming down from a
Okay.
spacecraft. So when we start downloading things, you have to assign them a priority. So we'll say like capture and download an image from the selfies, and then you have to give that a priority. And so if you started one download, you could while that image is still downloading, you could take another image and give that a higher priority, and then that download would then supersede your existing download.
Got it.
Telemetry doesn't use the same prioritization. It's instead just always interwoven with the download at a fixed rate, because we always are going to want like some critical flags from a spacecraft, because these downloads can take days or weeks.
Yep.
So we can't just use up all of our bandwidth downloading images. We still gotta know what's going on.
Cool. And then we have another one from Chris, and I think this is going to be for you, Emerson. If DeepSpace 2 went forward with the same propulsion system, chemical, as Odin, how would the build have changed?
So, well, first of all, I don't think we would ever have wanted to do that. But
It's the right answer.
But let's say it had. Let's say we had no choice. Since we're considering going to, we want to maximize the amount of targets that we could possibly get to. That would mean that we would have to, if we wanted the same performance out of DeepSpace 2, it would mean that we need a lot more propellant, like a lot more. And what this means is that we might have to potentially increase the size of DeepSpace 2 to accommodate all of this propellant, but increasing like we're already kind of size constrained, and increasing the size naturally also means increasing the mass of it, and we're already kind of mass constrained. So it's this kind of vicious cycle where it just leads to just not a good time. Like, and like on top of that, like even looking down into the future, at future missions, we also want to be able to carry instruments in future missions, which are very power hungry. Like a lot of the refinery and a lot of the mining side of these things are very power hungry. And so this kind of like eliminates two birds with one stone in that we're now kind of forced to create these very large solar panels and solve a lot of these issues that come with these very large panels ahead of time, so that at the next mission we already have very large panels, a lot of power that we can put to use into the instruments or into the thrusters or these different things. So electric propulsion all the way for these kind of deep space missions where you need very high efficiency and you want to maintain your mass to be as low as possible.
Awesome. All right. Well, that's all we have for today. Thank you, Kieran. Thank you, Emerson, for talking us through how a gimbal makes this whole thing work, because I'm sure no one was really thinking about how a gimbal was going to be a whole episode topic. But
Thanks for having us.
Yeah,
we did
thank you,
it. This
Chad.
was awesome. Thank you very much. And then we'll catch you next week, and maybe we'll have Matt back on, but it's sort of nice not having him here. I didn't say that out loud. All right. Have a great week. Catch you next week.